let's try to draw this configuration. So we have our digital IC. And here we have our analog IC. VDD pin and ground pin. Suppose this is somewhere here, our connector. And then out of the connector somewhere we have somewhere here our battery. And the green board is our printed circuit board. Clear? So, okay. So let's suppose inside of this digital IC we have quite a lot of CMOS gates. They are all switching at the same time at a certain frequency, 16 megahertz. So if we are placing a current probe on an oscilloscope and if we are monitoring the current, any idea how the current would look like?
We have a lot of spikes in probe.
Most probably the current would look like this. At the repetition rate of 16 megahertz, if you're driving this at 16 megahertz, we have these big current spikes. Current spikes are coming from crowbar current, dynamic switching current, and all the combinations of that. Okay, so what's the problem? The problem is that these current spikes are now flowing out of the battery. Let's draw it. All over here, pin, lead frame, bond wire, microchip, bond wire, lead frame, and then out of the ground pin and back to the battery. So this is the way how the current is flowing. Okay, so big current loop. So this is printed circuit board trace, As I mentioned, you mentioned it, the printed circuit board traces are made of copper, so they have a specific resistance. So we can include also some resistances. So we can also measure, for example, the resistance from here to here. This gives us a certain resistor, 0.3 ohm. We can also measure the resistance from here to here. This also gives us, in this equivalent circuitry, another resistor. Same here. And also same here. So we have an, let's call it parasitic resistance. It's clear? But, was also mentioned today, there is also a parasitic inductance because the current is flowing in a loop and our loop is pretty big. Unfortunately, it's pretty big. So the whole loop area is forming a inductance. And we can split the inductance in several branches. So we can give this branch here an inductance, this an inductance, this an inductance, this an inductance. So we can also place a so-called mutual inductance, sorry, equivalent, no, yeah, was also not the right word that I was looking for, missing the word, partial inductance, this was the word, for this branch here, and the partial inductance here, and then also over there, and also over there. So this is just a very simple equivalent circuitry. In reality, there are stray capacitances. The thing is, what I think is very often we get the impression when we are reading some textbooks that there is also a certain inductance of a printed circuit board trace. Or maybe you've already heard something like a 1 millimeter bond wire has an inductance of 7 nanohenry or something. Have you ever heard of this? That a piece of bond wire has a certain inductance? Or a printed circuit board trace, 1 centimeter is 7 nanohenry or something? Yeah? It's interesting because actually it's completely stupid. 1 millimeter of bond wire has definitely a certain resistance. I think it's clear because it's made of gold. Gold has a specific resistance. It has a specific length, a specific diameter. So it's obvious that there is a resistance. But where does the inductance come from? If I just have a piece of bond wire, like let's imagine this is the piece of bond wire, or this is my piece of printed circuit board placed in a certain distance over the signal return plane. So where does the inductance come from? Yeah, this is the thing. So just a sentence that 1 centimeter of printed circuit board trace has a certain inductance is completely stupid because 1 centimeter of printed circuit board trace or 1 centimeter of bond wire doesn't have any kind of inductance. Only if this printed circuit board trace or the bond wire is connected in a loop. And here we have a very big loop. And one small fraction of the big loop is related to the bond wire. Then we can somehow calculate what is the total inductance of the whole loop. This might be, I don't know, 1 microhenry, say it. And then it's pretty clear that this small fraction of the total loop length, loop area, is also related to this small part of the bond wire. And then out of several statistics and measurements, they came to the conclusion that in roughly all the cases, 1 millimeter bond wire or 1 centimeter of this printed circuit board trace has 7 nanohenries or 3 nanohenries or whatever is written in the textbooks. And this gives you some kind of rule of thumb. But in reality, it's completely stupid because it really depends on how big is this loop. Because I hope you agree that there is a difference in this parasitic inductance here, if the loop is that big or if I'm placing the traces very close together. So this general rule, it's 1 centimeter, so therefore it's 7 nanohenry, is not always true because it depends on how big is the loop. Okay, just to clarify the things. So, okay, but I hope you agree that we have a very big loop and 1 fraction of the loop area can be related to a partial inductance that has some nanohenry. Okay, good. So what's the point? The point is we have these current spikes. They are flowing now in the loop area generated by the switching activity. And what does the current do if it's flowing here along the ground path? Same for the VDD path. It causes a voltage drop. So every time the current rises here, the current flows also here, generating a voltage drop. Okay, it's not that critical because the resistance is not big. But here comes the point. In series to this resistance, in this very simple equivalent circuitry, we have an inductance. The inductance, we said the whole inductance is 1 microhenry, so maybe this thing here is 25 nanohenry. Good guess. And now we have a big di over dt. And we have a voltage drop. And this voltage drop is usually much, much bigger than this voltage drop. And we also have a voltage drop here and a voltage drop there, and the same in the power supply. So, but here comes the problem with this galvanic coupling. This is our battery. So here at the plus pole we have whatever 9 volt. Here at the minus pole we have our 0 volt reference. So this is our ground. So here we assume 0 volt. This is our analog IC that is connected by the ground pin to the ground of our printed circuit board. But is this point here also 0 volt, as it should be? Hope you agree. Definitely not. What's happening here? This ground node in relation to this ground node is jumping up and down at 16 megahertz by the voltage drops here. And this voltage drop is not just microvolts. This can be hundreds of millivolts or even volts. So now if this is our sensitive analog IC, what happens to an analog IC if the ground is not 0 volt, if the ground is jumping up and down with 16 megahertz? Maybe the internal analog to digital converter is not that accurate anymore. Especially because very often we also have some reference pins that are also connected to a stable potential. And if the stable potential is jumping up and down, then also the reference is jumping up and down. So it's pretty clear that we have generated, in this case, galvanic coupling from a digital part, digital IC, to the analog part. So this thing here is called ground bouncing because the ground is bouncing up and down. And here we have exactly the same thing because the same current that flows here is also flowing here. So we're also generating a voltage bounce. And then also the voltage supply of our analog chip is not stable 9 volts. It's 9 volt and jumping up and down at 16 megahertz. I think it's clear. So here it's voltage bouncing, here it's ground bouncing. Maybe you've heard ground bouncing somewhere. Yeah, and this is one of the main problems that we have, that switching activities from the digital part are coupling by a galvanic coupling mode into the analog part, into a sensitive analog circuitry. So now let's check how much time we have, because now can you give me 3 additional minutes? Because now comes the important thing, what can we do in order to avoid this EMC problem? I think the generation of the EMC problem is clear, hopefully. But now it's up to you. So let's suppose you're an engineer in a microelectronic company. The customer is complaining that the electromagnetic emission or the coupling or whatever is too big, and it's your job to solve the problem. So what are you doing in order to solve the problem? Use capacitances everywhere. Yeah, there is a reason why I have not drawn capacitors. So would you design a circuitry like this? No, definitely not. Because you need decoupling capacitors in order to stabilize the power supply. And now we see that the decoupling capacitors has many purposes. So on the one hand, it stabilizes the power supply between these two nodes. So we also need a decoupling capacitor, definitely also here at the analog part, which should be placed, sorry for my bad drawing, really between the pins. Okay, what does the decoupling capacitor do and why does it help? Because now this switching activity that is generated here, so these current spikes, if you have designed it in the right way, they can come out of the decoupling capacitor. So the way the high frequency current is flowing is not over the whole loop area anymore, because there are inductances and resistances, so the impedance in the direction to the battery is much bigger than the impedance that we have over there over the capacitor. And the capacitor also acts as a charge storage element, so for the capacitor it's no problem to provide currents at this rate. So if we have designed it in a proper way, then hopefully all the high frequency currents are flowing only in this small loop area and not anymore of the big loop area. Big loop area, big magnetic field coupling out. So here we have small loop area, smaller magnetic field that is coupling out. Okay, so decoupling capacitor definitely helps and should be placed as close as possible. Other things? Exactly, why should the loop area be that big? So maybe we can make the loop area smaller. Small loop area, small parasitic inductance, small voltage drop. So place the VDD and ground connection close together. Preferably use a printed circuit board design, a multi-layer printed circuit board design, where one layer is acting as a signal return layer and the other one next to each other, at a very close distance, is a very big layer acting as a VDD layer. This gives you an additional benefit because this is also a very good capacitor. And this is the best decoupling capacitor that comes for free. And then the loop area is the smallest that you can get. Okay, so shrinking everything and making the loop area small. Okay, any other ideas?
Use a voltage regulator at the input after the battery.
Okay, yeah, also possible. After the battery, or maybe also directly here to decouple somewhere, but this is a quite expensive solution. Okay.
I mean, I don't know if you can do it on the PCB, but usually you have those star connections to one ground so that you don't have a long path where they are coming in.
Okay, so what about cutting this ground connection here and connecting the grounds over there to a kind of star connection, and also here for the VDD. Yeah, it's not that easy to draw anymore in my drawing. So then this loop here is not sharing the same resistance and inductance anymore with the digital loop, so separating the domains a little bit. Okay, very good. Sometimes people are also using additional filtering elements in the power supply because the decoupling capacitor, as I mentioned last time, is not fully effective over the whole frequency range. It's only low impedant at a certain frequency range around the resonance frequency. So still some DI over the D current spikes or high frequency content will come out of the big loop. And in order to avoid that, some designers are also designing here a ferrite bead to have a high impedance in this direction so that more current is drawing out of the capacitor. Okay, anything else? There is a reason why I have drawn chips with this configuration, VDD here and ground there.
Those pins closer together.
Yeah, put the pins closer together. Any idea why they have placed this VDD and ground pins in the most stupid way they could have been placed, especially for the old-fashioned 47 high-speed CMOS designs?
Because it was done like this.
Yeah, but there must be a special reason why from the EMC point of view, it's completely stupid. Also, I hope you agree that this gives the biggest loop area, the biggest parasitic inductance, the longest bond wires, the biggest inductances of the bond wires, and the biggest voltage drops across the bond wires, and the biggest ground bouncing and VDD bouncing. So from the EMC perspective, nobody would do that. But it started in the 1960s, 70s, and maybe they didn't thought about EMC during these days. Okay, it's a good excuse. Also the solution would be place the VDD and ground pins as close together as possible and place them at the location where the smallest loop area, especially with the lead frame and the bond wires, will be possible. So very often we are placing VDD and ground here, then we have the lead frame and then bond wires, and then the loop area is that small compared to this one. Okay, now the explanation why they used this stupid configuration. Yeah, the old printed circuit boards from the first computers from the 1970s, they really looked like this. So this is the printed circuit board. There is a connector. Yeah, okay. There's the connector with all the and so on connector pins. So imagine that there is a printed circuit board that is stuck into a kind of back plane. And then on the printed circuit board, the old ones, they had one IC next to the other to place as many digital ICs on one printed circuit board as possible. There were no multi-layer printed circuit boards. They very often had only 2 layers. And then it was very simple to route VDD and ground, because you can route a big ground trace here and a big VDD trace over there. And then within between you can then connect, and then somewhere below the ICs, all the digital inputs and outputs. And this was the only reason why they have placed the VDD pin here and the ground pin there. Definitely not for EMC reasons. Okay, so very good solution would be place VDD and ground next to each other. Okay, so very good. So you solved your EMC problem. Hopefully, it was a pleasure discussing with you how to solve EMC problems. Next time we are discussing then a little bit further what kind of additional couplings we have and how we can solve further EMC problems. Thank you very much. Looking forward to seeing you next time.